like with the hard drive and stuff.
Yeah, I found it.
Is there a reason why you're still using Windows?
Because they installed a NVIDIA driver, an NVIDIA video card, and I was no longer able to use the screen in any usable fashion. It locked down the main screen to 640 by 480, the resolution, which is not really usable in the class.
Yeah.
All right. So, got several things to do. The first thing is I'm going to pass the test back to you guys. It's not graded yet, but I did use about 2 hours last night to scan everything. So at least they're all digitized. So now you can have your test back, and I can basically do the correction based on the scanned version. So that's good. I have to justify all these purchases. Otherwise my wife would ask, what is that? It's a scanner. Why do you need a scanner? Because. Why do you need a scanner that can scan like 60 pages in a minute?
50 isn't 60.
Okay, but before I pass it, is anyone in the class objecting to having this passed around in the class? There are no scores on it, and the first page is really just your name, so there's nothing, no grades on it whatsoever. But is there any objection? Okay, so if there's no objection, I'm going to pass it back to you guys and let it pass in the class. So this way I can spend more time, talking about topics related to this class, and less time, butchering last name and first names of people. Because as I entered the names into the roll sheet, I was going like, no way I'm going to pronounce this one correctly. All right. So what we'll do today is we'll finish up the algorithm to find prime factors of a number, and we will prove a theorem. Okay, so maybe I should erase this, because otherwise it's giving away what we'll be talking about soon. And I should use my left hand so that my Fitbit will be convinced that I'm doing exercise. That's at least a minute of rigorous.
You just powered up the watch.
Yep. That's at least a few joules right there. All right. So switch to, well, I don't even need to switch to that portion, but I do need to start fresh. So I'm gonna erase all this stuff and then start from scratch again. So let's get rid of all this stuff. All right. Okay. So let's go ahead and get started again. We'll start with finding a prime factor this time, because last time we already talked about an algorithm that finds all the prime factors of a particular number. But what we have not talked about is how do we find a single prime factor, which is which is indicated by a statement in the algorithm. Find prime factor f of n, which states what needs to be done, but not how it is done. So what we'll do today first is to figure out, okay, how do we find a prime factor given the number n, and then we'll go from there. Okay? And to do that, it doesn't help if you start with numbers that are easy to deal with. So what we'll do is we'll start with numbers that are not so easy to deal with, and then see if we can find a systematic way to do it. Okay, do you guys have any questions? Okay. Okay, so let's go ahead and start with, a number that seems, okay, is that divisible by, that's pretty good. Okay, so we'll pick this number here, because I don't want to pick any number that is small or a number that you can memorize from the multiplication table. Even numbers like 91, it's not useful because you can memorize, you recall from memory that 91 is 7 times 13. Okay, so even though it looks like a prime number, it's not, but you already know it is not a prime number. So we'll start with this one here, and then we'll do a very systematic way. We'll use a systematic method to find its prime factor. Okay, we just need to find one because we already have the logic to find all of the prime factors, but we need a sub-method to find just one factor. We'll start with 2, which doesn't seem to be very smart because we know this number is odd to begin with. It cannot possibly be divisible by 2, but we want a systematic way. And this is a very systematic way because we can just say, okay, start with this number, divide it by whatever number is to the left-hand side of this column. And it has a remainder of 1. Okay, not very surprising, right? But that's okay, because now that I have set up one cell to do this, I can now just expand it and make it work on all the other numbers. I'm just hoping that I'm not going to end up with a very small prime number, which would be kind of disappointing. Nope, that's good. Let's do it this way. Okay, I think by this time we should be okay. Okay, from the previous class, somebody told me that I can use filter. So we'll just use an auto filter feature here. And we find that, 0 is here somewhere. So I just have to unhide all of the cells except for the 0. And it turns out that 191 is a prime factor of this number. Okay, so it does have a prime factor. It is a composite number. It's not a prime number itself, but it took us a while to find that. Okay, so let's go back and take away the filter so we can look at the spreadsheet itself without the filter. And from here, we want to say, well, is this method systematic? Well, anything that I can use, that method of highlighting 2 cells and then just drag it down until we find a 0, I would say that's fairly systematic. Okay, something that can be done automatically. Any questions I can answer? Okay. Huh?
Just looking through the test.
Oh, okay. Scanning through, finding your name. Okay. All right. So the next thing we want to do is, this is actually quite interesting. Look at this pattern here, because they're all it's just a sequence of 1, 2, 3, 4, 5. For these potential factors of 2, 3, 4, 5, and 6. But anyway, so this is a fairly systematic way to do it. And what we'll do first is to find out, how do we write an algorithm to do just that, okay, to do what I just did with a spreadsheet. And to do that, I'm going to go through revisions. So the first revision is to say, do you think this method is just a sequence, like we do this step 1, step 2, step 3, and we are done? Or do you think this is repetitive? We are doing something over and over again. Which one, is it a sequence, just 1, 2, 3, 4, we're done? Or is it a sequence, let's do this again and again and again and again. Oh, okay, now we can exit. First case or second case? It's a second case. Okay, it's repetitive in nature. Okay, but that's good. We can just identify that it is repetitive. Before we can identify whether to use a pre-checking loop or post-checking loop, I'll just use, it is some kind of a loop to say that, okay, we're dealing with a loop here. Do we want to exit at some point? Because there are loops that do not exit, but most loops do. So in this case, are we exiting? The objective of the algorithm is to find a prime factor given a particular number. So I would imagine that we have to exit at some point. Because the worst case is the number itself is prime, then we will still exit when we get to that number itself. Okay? So we do exit at some point, and what is the condition that has to be true when we exit? What is the exit condition?
The remainder has to be 0.
The remainder is 0. Okay? So, okay. How about a factor is found? Okay. Which is the same thing. Because a lot of times, you guys are a little bit ahead of me already, because you already know, okay, we can look at the remainder. So in revision 2, then we'll start to look at it in a more mathematical way. In other words, we say when the remainder of n divided by f is 0. Is that okay? Is that a big jump? In other words, when I transitioned from a factor is found as an exit condition to the remainder of n divided by f is 0, is that a big leap? conceptually. Not too bad, right? I mean, it's not too big of a leap. Okay. And that's one thing that we want to do, is to make sure that we are not making big, huge jumps. Okay. So we'll look at revision 3. Revision 3, we'll look at this and say, is there a better way to say the remainder of n divided by f is 0? Can we express it in a way that a programming language can understand? Well, as it turns out, there is an operator called a mod operator, and we can use it in this case. Okay, let's take a closer look at n mod f. Mod in this case is taking the place of a division symbol, and the operation mod is giving me the remainder of a division, not the quotient. So when we use n/f, we are interested in the quotient of a division, but when we say n mod f, we're interested in the remainder of the division, not the quotient. Are there any questions about the mod operator? Yep.
Can you repeat the definition again?
It's the remainder. It's the remainder of a division. So in this case, n mod f is the remainder of n divided by f. So let's go through a few examples of mods. Okay. So let's do some really kind of not so interesting ones first. What is 7 mod 2? What is the remainder of 7 divided by 2?
1.
1. Okay. What about 6 mod 2?
0.
It's a 0 because the remainder is 0. What about 17 mod 5? 2. Very good. And what is 1 mod 5?
13. I don't know.
0, right? It goes into.
What is the remainder of 1 divided by 5?
Oh, reverse. 1/5.
Hmm? No, I still have not heard the right answer. Come on, it's
It does not exist.
okay. So the thing is like this. Okay, I have 1 candy, right?
All right.
And with that 1 candy, I want to distribute it evenly to 5 kids.
Tell them to feel that.
But I cannot give a kid, Okay, excuse me. Do you guys have a question I can answer?
I got a little confused
Sorry.
on the actual model.
Okay. It's the remainder of 7 divided by 2. It's the remainder of a division.
Oh.
Okay? All right. So getting back to 1 mod 5. The remainder of 1 divided by 5. Okay? What is it? I have 1 candy. There are 5 kids. I'm supposed to give each kid a whole number of candies. And the remainder is whatever I have left in my hand. Well, since there are 5 kids and only got 1 candy, I'm going to tell the kids, you are not going to get the candy from me. So each kid would have 0 candies, and I have 1 left in my hand. So the remainder is actually 1. 1 mod 5 has a result of 1. All right. If this doesn't seem to make any sense, let's go ahead and take a look at the long division method. In the long division, the part or the thing that is being divided is called a dividend. This is called the divisor. This is the usual thing, which is the quotient. So in most divisions, we are more interested in the quotient than the remainder. But in this case, we are more interested in the remainder in a division. Right? So are there any questions about the notation of which part is which part in the division? This is okay? All right. But how do these 4 terms relate to each other? That's the other question. Okay, I can define it like this, but in the mathematical equation, how do they relate to each other? Well, they relate like this. The dividend is actually expressed as the divisor times the quotient plus the remainder. Is that making any sense? So when we have 1 divided by 5, having 0 as a quotient and 1 as a remainder, let's plug in these numbers. 1 is our dividend, 5 is our divisor, 0 is our quotient. 5 times 0 is 0. And this other one is my remainder. So we get 1 equals to 1. So the equation holds for this particular division. Okay. So are there any questions about why n mod 5, why 1 mod 5 is 1? No questions? Okay. All right. Okay, so I think we sufficiently understand what a mod operator will do. So let's move on. Now, this one is actually important. Revision 3 is actually very important because it summarizes the exit condition here. When you look at the exit condition, it is n mod f equals to 0, which is the remainder of n divided by f is 0. In order to make this true, which one can we change? Can we change the constant 0? No, because if it's just a constant, we cannot change it. We cannot change the 0. So we can only change variables. We have 2 variables in this case. Can I change n? Well, remember what is the role of n in this case. N is the number that I'm supposed to find a prime factor of, right? So changing n is the same thing as somebody asked me, to find a prime factor of 101, and I say, well, that's too difficult for me. But I can tell you that 2 is a factor of 4. Is that answering the question?
No.
No. So I cannot change the question itself. So that means n itself cannot be changed either. So n cannot be changed. 0 cannot be changed. What else can be changed here? Variable f is the only one I can change. So that reasoning is important because it tells me that in each iteration, I'm probably doing something to f, but not n, and the constant 0 obviously I cannot do anything about it either. Okay? So this is actually very important because of this I can make the observation that f needs to be changed somehow in each iteration so that the condition will eventually be true. Is that making any sense? Okay. So I'm trying to kind of tell you guys how to write an algorithm or come up with ideas of how to write an algorithm in a step-by-step basis. All right. So now that we know f is going to be changed in each iteration, let's go back to the spreadsheet and see if it's giving us any hints of how f is changed, in each iteration. What do you think? By the way, which column, except for the first row, which column is representing f?
A.
Column A. And if you look at column A, how does one row relate to the row before?
F plus 1.
It's just adding 1 to it. Okay? So f gets f plus 1 is what we do for each iteration. We're just bumping up the value of f for each iteration until f becomes a prime factor, becomes a factor of n. Okay? So that's great. Okay? That's our revision 4. We're almost there. Let's take a look at revision 5, because in revision 5, we have to kind of indicate, but what is the first value that we are supposed to test with? In other words, in this case, we want to ask the question, what is the smallest prime number? 2 is the smallest prime number because 1 is not even a prime number to begin with. So 2 is a prime number. So what I'll do in revision 5 is not to initialize f, but to indicate that the first value of f for the expression, for the Boolean expression is 2. Okay. The rest we can just copy. All right. So now we are ready to come up with the actual algorithm. To come up with the actual algorithm, you can see that we have a loop. We know what f is supposed to start with. We know the exit condition. We have everything that we need to actually come up with either a pre-checking loop or a post-checking loop. And in this case, both will work, except one is slightly better. So we'll present one first. So in this one, we'll say repeat, and use repeat until, which is the easier way to do the conversion. So I'm going to do the copy and paste here, except I change this part to just until. And in this case, how should I initialize f? 2? Now, if I put a 2 here, that's going to be a problem, because if I put a 2 here, what is the value of f by the time I get to until?
3.
It's going to be at least 3, right? Because this is a post-checking loop, which means we perform at least one quote-unquote iteration before we get to the condition. So if we initialize if we initialize f to 2, and then we perform f gets f plus 1, by the time we get to until, f has a value of 3 already. So that's not good, because we cannot find prime factors of 2 anymore. So that means we have to adjust how we initialize f to 1. Then by the time we get to the comparison, f would start with a value of 2. Okay, so that works. It's okay. In revision 6b, we are going to use a pre-checking loop. A pre-checking loop starts with the condition itself, and in this case, we have to negate the condition. In other words, we have to say, when do we stay in the loop? When n mod f does not equal to 0, we have not found the prime factor, stay in the loop. Okay, so in this case, how should I initialize f? No,
2.
Yep, just 2. Okay, all right. Revision 6a is going to work. Revision 6b is also going to work. The question is, which one is better? 6b is better? Why is 6b better than for 6a? I think you know the reason. Just
last class.
Hmm?
Because I heard it in the last class.
But there's a reason why 6b is a little bit better.
You don't get confused about the assignment beforehand?
It's easy to see what is the first value that you're using for the condition, right? In other words, on the line of the while, it's very clear that the first number that you start with is 2. But in revision 6a, it is not as clear, because you have to say, okay, it starts with 1, but then we add 1 to it, it becomes 2. Okay? So that's why 6b is the preferred solution. Even though both will work, 6b is a better solution. All right, so that's good. What we'll do next is we'll plug it in and just run a few traces, and then we'll find a way to optimize it. So we'll start with f gets 2 while n mod f does not equal to 0. Do the following: f gets f plus 1, and while. And we'll just trace. We'll have 2 test cases. Let's indent one window. And then we'll trace it. Let's try 15, for n, and f is unknown to begin with, and this is my precondition. In this particular case, we have to start with a value in n because we're trying to find the prime factor of n. So we cannot start with an unknown value. Right? So we'll go ahead and trace it. On line 1, f gets initialized to 2. On line 2, we evaluate the condition. N is 15. F is 2, n mod f is the remainder of 15 divided by 2 is 1. 1 is different from 0 is true. Okay. We go to line 3. Line 3 adds 1 to f. F goes from 2 to 3. We go back to line 2. N is 15. The remainder of 15 divided by 3, which is f, is 0. 0 is different from 0 is false, and we're done. Okay, great. Not complicated, pretty quick. And let's look at the next example. The next example changes n to 13, which is a prime number, and then we'll see what happens in this case. Line 1 initializes f to 2. Line 2 evaluates the condition. N mod f, which is 13 divided by 2, the remainder of. What is the remainder of 13 divided by 2? It's 1. So 1 is different from 0 is
True.
True. 1 is different from 0 is true. Go to line 3, we add 1 to f. And I'm going to be a little bit lazy. I'm just going to say this is equal to this number plus 1, which is 3. We go back to line 2, and then we reevaluate this condition. n mod f is different from 0 is true. And those, so we kind of repeat this process again. So here is why I can do this. Because the increment is done by the script itself, I can actually automate the evaluation of the expression as well. It's just a little bit more involved. Does anyone want to see how that can be done?
Why not?
Okay, sure. Well, this is scripting, right? But this is a programming class, and this is definitely related to programming. All right, so we'll use concatenate. Concatenate. How do we do concatenation? Joining strings? Nope. All right, I'm gonna cheat. Look it up. All right, so we're looking at a string function, text function, and we want to do concatenation. Oh, okay, I misspelled. That's fine. All right, so we say concatenation, or concatenate. There we go. So we can take on different pieces. The first piece is just going to be the string itself, which is n mod f is different from 0. The whole thing is okay. And then the second part is going to be the actual evaluation. So the actual evaluation is based on this number here, or the mod of that. So we'll be saying mod of this number by, let's see, by this number here. With this one, we have to use a $ for the 2 because otherwise it will float with the cell that is being copied. This way it won't float with it. Okay. And we want to see whether this is non-zero, so we have a comparison of 0 here. So let's see if that works. Okay, it does work, except it wants to look at this whole thing as a 1. So we'll put a conditional statement around this whole thing so that it will print either true or false. Go. All right, so now we are all set up to go because now we can just wrong key.
Reverse.
Control Z. There we go. All right. Of course, there's a better way to do this. I can copy and paste this entire block and just, and it's a lot faster this way. And one more time and we're done, right? See, it tells me that it's false this time because 13 divided by 13 has a remainder of 0. And from line 2, I will get to post.
So we have to make it so that way if f ever becomes equal to or greater than than n, then it cuts. Otherwise, it just keeps going.
Yep. All right. Yep. So obviously, I'm not going to require you guys to use these features of Excel or any spreadsheet. But I think it is good to have the exposure. Okay, I think it's really useful that people understand what a spreadsheet is. It's not really just a table for formatting purposes. Its main purpose is actually for calculations. So you can use it to balance your income and expenses and whatnot. There are other things we can do too. There are a lot of things you can do with a spreadsheet. How many people in this class is kind of like a regular user of using spreadsheets?
I see them a lot. My husband uses them a lot.
Okay. Does he use it for?
Don't spend any more money.
Yeah, we use it for all kinds of stuff. My wife uses it to analyze all kinds of stuff. Anything to do with numbers. We can use it. It's a gigantic calculator basically. That's what it is. But you can also use it to plot charts and stuff like that. All right. So this is how this particular algorithm runs. We have to go all the way up to 13 to understand that 13 is a prime number itself. Yep.
Would it understand if you did the exclamation and equals?
Exclamation point and
That's the
equal.
other way.
It's the same thing as a not equal.
It would still work.
Not in this case because the spreadsheet only understands
That way.
greater than, less than as not equal to. So if you put in the C representation of not equal to, which is exclamation point and an equal, it's not going to work. Yeah. All right. So now that we understand, how the algorithm works, let me tell you, I can put in a simple optimization, and with that simple optimization, by the time we test that 4 is not a prime factor of 13, I can stop right there and say that 13 is a prime number. If I'm testing 101, by the time I test to 11, I can conclude 101 is a prime number. No need to go any further. Would that be a worthwhile optimization? Yeah. But first of all, before we do the actual optimization on the algorithm, we need to know that the optimization technique itself, or the theorem behind the optimization technique, is true. Okay? We have to make sure that that is true all the time before we actually make use of it. So this is when we switch to the notepad here, and I'll present to you, something that I'm going to claim. Okay? So let's say that these are the restrictions. So let's say we have a restriction that let's pick a number a. Okay, a is a positive integer. Assume b is the same thing. B is another, well, potentially the same. Okay, b is a positive integer. A is a positive integer. We define p as the product, a times b. Are there any questions about these three statements? Give me any number a, which is a positive integer, 2, 5, 10, even 1 will work. Give me any b that is also a positive integer, okay? And define p to be the product of those two. Is that okay so far? Okay. Assuming these things are all, playing by these rules, TAC has a claim to make, okay? TAC claims that the following has to be true. So TAC claims that p has to be less than or equal to a times a, or p is less than or equal to b times b has to be true. That's what I'm going to claim. Okay. Is my claim true all the time? Pick any number a, pick any number b, define p accordingly, and this has to be true. Can someone prove me wrong in the next 5 minutes? Yep. What about 1? 1 is less than or equal to 1 times 1 is true.
That would be like false, right?
Huh?
You want us to prove it false? Or
What?
You want us to prove it false?
Yeah. Can you prove me wrong? This is my claim.
Using
And if I say that if you can prove me wrong, I'll give you $1 million. What are you gonna do? You want to prove me wrong, right?
It's an idea.
Okay, so come on, prove me wrong. Okay. Well, you may not be able to do it. Oh, yep, go ahead. Go ahead.
Are we allowed to use
Withdrawn,
I?
right? Counter example withdrawn.
Are we allowed to use I as in the square root of -1?
No, they have to be integers, non-complex integers. Yep.
Why can't it be a equals 1, b equals 2?
If a equals 1, b equals 2, then p is 2, right? Then the second one will be true because p is less than or equal to 4. Yep. It's hard to make it false. Okay.
So this is or
let's
not and.
so let's just say that my requirement is no longer over the next 5 minutes. Okay. I will give you as long as it takes for you guys to prove me wrong. Okay. But that means that I cannot proceed after this point for this class. So I'll just make the conclusion that you cannot prove me wrong. Okay, but somebody in the class will say, "But that's cheating." Okay, you're just taking that $1 million away from me because I cannot prove you wrong in 5 minutes. So I'll go ahead and prove that you cannot prove me wrong. Okay. All right. Well, this is a mathematical proof. Okay, and the mathematical proof that I'm going to use in this case is called proof by contradiction. Now, proof by contradiction is a funny name because it just doesn't make sense, right? How do you prove something right by contradiction? I mean, doesn't that kind of implies that it is wrong to begin with, proof by contradiction? So let's go ahead and take a look at what is proof by contradiction. Okay, so prove. I'm trying to think of, should I use the verb or the noun here? I think it's the verb. Proof by contradiction works like this. Okay?
Well, it's mathematical, so it'd probably be proof with an F.
With an F. It depends on whether you're referring to the technique.
Well, when we did stuff like this in a couple
Okay.
of calculus classes, we did use
Okay.
the F for.
Okay. So let's use the noun. Proof by contradiction starts with the negation of the claim. In other words, in this case, you're basically saying, let's say tag was wrong. Okay? So the question now is, what if I was wrong? What kind of bad things can possibly happen if I was wrong? Okay, if I was wrong, it means someone can find a pair of values A and B such that what I claim has to be true for everything is not true for this pair. This is false. Okay, let's stop here and make sure that everybody understands what it means when I get to this point. Okay, I claim that whatever. Okay, I have to go back to here to point this out. So I claim that this has to be true as long as A is a positive integer, B is a positive integer, and P is defined as a product. This has to be true. So to prove me wrong means that somebody can find me a value for an A, a value for B. They're still positive integers. Define P to be the product, and somehow the claim is false. Is that working out okay so far? Okay. Does everybody understand what it means when I'm wrong in this case? Okay. The claim is false. Okay. For at least one counterexample. Is that okay? All right. So if that is true, okay, and I don't even need to know exactly what value of A and what value of B will make my claim false. I'm just saying that let's say it does exist. Okay, let's say such a pair of values exists. Okay, what can be the result? What can be so bad about that? Okay, all right. So what we'll do first is we'll say, well, just like in arithmetic, you can do a negation on both sides of an equation. I can do the same thing with logic. In other words, I can just say a not here to one side and apply the not to the other side, and the equality should still hold. So in this case, we have this entire side inside the negation, and then we have the simple entire side on the other side also inside the negation. Is that okay so far? Is everybody convinced that if I perform a negation on both sides, then the equality should still be holding? Okay, all right. One side is really easy to deal with. The left-hand side is easy. Excuse me, the right-hand side is easy. The left-hand side, not so easy. So I'm just going to copy and paste this part here. And then the other side is just, hey, not false is true. We know that. Okay, that's good. Now we look at this mess here and say, but what can we do about this? I mean, this looks kind of nasty. So, well, there are a few things we can do. So the first thing we'll do is we'll apply what we call De Morgan's law. All right. Is anyone going to a computer or electrical engineering program? Okay, there are a few. And those of you, will probably have to use De Morgan's law a lot. Okay? Because De Morgan's law is magical. It can transform a conjunction into a disjunction, and it transforms a disjunction into a conjunction. Okay, it works like this, or at least I claim that it works like this. Okay. If you look at the negation of, okay, I used A and B already, let's use X and Y in this case. So if I take a negation of X or Y, I claim that this is really the same thing as not X and not Y. X and Y being Boolean values. First of all, does it seem to make sense to you just from the intuitive perspective? It seems to make sense, right? But does it work out in all cases? Well, we can use a truth table to prove that it does work in all cases. X is a Boolean variable. Y is a Boolean variable. They're independent. So that means when x is true, y can be true or false. When x is false, when x is false, y can be true and true or false. So I have now enumerated all the possible cases between x and y. So it's time to work out, the expressions themselves. X is true, y is true, the disjunction is true, not true is false. X is true, y is false. X is true, y is false, true or false is true, not true is false. X is false, y is true, false or true is true, not true is false. False, false, false or false is false, not false is true. Is that okay? Now we need to work out this column. X is true, y is true, not true is false, not true is false. False and false is false. We have true, false, not true is false, not false is true, so we have false and true is false. On the third row we have false, true, so we have not false is true, not true is false, we have true and false, which is false. And then the last one is false, false, not false is true, not false is true, we have true and true, which is true. So now I have just proven that one expression is equivalent to the other expression. Because if you look at this column and look at this column here, for each row of all the combinations of x and y, they are the same. Okay, so this is how you can prove a Boolean expression is truly equivalent to another expression. They may look alike, they may look intuitive, or they may not even look intuitive, but as long as the columns are matching up, they are still equivalent. Are we doing okay so far with this table? So using that table, which is called De Morgan's law, I can now transform this negation into something that is a little bit easier to handle, because I can distribute the negation to inside the disjunction, but turn the disjunction into a conjunction. So this becomes the negation of P is less than or equal to A times A, and then the negation of P is less than or equal to B times B. I got one too many multiplication here. Is that okay? Does everybody see how the transformation, is what happens? Essentially, we have this entire chunk being our x on the whiteboard, and then this entire chunk being our y on the whiteboard. And I just performed the transformation. Is that okay? All right. So the next step is to take away the negation and say, is there an easier way to say it is not the case that P is less than or equal to A times A?
P is greater.
P is greater than A times A? Okay, that's a pretty easy way to re-express the same thing. Is everybody okay with this concept here? The negation of P is less than or equal to A times A is really saying the same thing as P is greater than A times A. Is that good? Okay. I can do the same thing with the other side. So we take away the negation and flip the comparison around to that. Is that still okay? I'm doing step by step here. Okay, I'm trying my best not to skip any steps. Okay. All right. So when we get to this point, then we have another theorem that we have to prove or at least understand before we go forward. So if I give you something like this, A is greater than B and B is greater than 0, okay? So A is greater than 0 too. And then we have C is greater than D and they're all greater than 0. Can I take the product of A and C and conclude that A times C is greater than B times D? Does that imply AC is greater than BD and they're all greater than 0?
No. Not
Yeah,
quite.
yeah, it makes sense. Okay, all right. So if we apply this to what we have on the on the projector, then we end up with something. So this implies the following. It implies P coming from the first comparison times P coming from the second comparison is greater than A times A coming from the first comparison times B coming from the second comparison. So this has to be true as well. Is that okay? Because I am just reapplying this technique here. Because we know that A is positive, B is positive. So the product of A times A has to be positive, B times B is positive. Is that okay? And as a P is also positive because it's the product of two positive integers. Is that okay? That doesn't seem too bad. I mean, everything seems to follow, step by step, logically, everything is good. So the next thing I'm going to do is to use the commutative law of multiplication and just switch the middle A and B around. I'm going to switch the order of these two around. In multiplication, you can switch the order all day long. It doesn't change the value of the product. So I can do this all day long and, shouldn't do anything. Yep.
Would it have to be P times P is greater than or equal to?
No, it's just greater than, because the conversion comes from here. So when you negate less than or equal to, the result is just greater than. Because equal to itself is negated as well. So you have to take that out of the equation. All right, so that by itself still doesn't look too bad until you figure out what is A times B. I'm putting parentheses around these just so that it becomes more clear. What is the definition of P again? A times B. Okay, so that means this A times B becomes P. The other A times B also becomes P. P times P is greater than P times P. Has to be false, right? So now we have a contradiction. Okay, something that I claim to be true is actually false. Okay, hold on a second here. The contradiction comes from negating my claim by saying that Tech was wrong in the first place. So if it's not possible that I was wrong in the first place, what is that actually saying?
That you were right.
That I was right. Yep. So I'm going to save you all the trouble for trying to find out, to come up with that counter example. Oh man, that goes at $1 million. Is that okay so far? I think you guys can make more than $1 million once you become a competent programmer and find a killer app like Angry Birds or Flappy Bird. Yeah, that's even better. I mean, that one was just weird. A really kind of bad program, and it got popular because the developer decided to not to do it anymore.
What was the actual highest bid? I know there were some crazy bids, but did someone actually pay?
The recorded one was 95,000.
So
They actually paid that.
for it.
But I'm not sure whether the transaction went through or not because eBay actually stopped it.
Oh, they did.
Yeah, they did.
Oh.
Yep. So this is the power of contradiction in the context of a mathematical proof. Just as a politically incorrect comment, contradiction, the whole concept of contradiction is also very powerful. For those of you who have not seen the movie Dogma, you should watch that movie to understand the power of contradiction. It can spell the end of the world as we know it. How many people have seen that movie? A few, okay.
Buddy Christ.
Hmm?
Buddy Christ.
George Carlin as Cardinal, right? I mean, that basically sets the whole tone of the movie. Having George Carlin as the Cardinal with a blessed golf club. Yes. So if you can get past the disclaimer of the movie, which is the first 2 or 3 minutes, with all that scrolling text, the rest of the movie should be okay. If you cannot get past the first 2 or 3 minutes and think that I cannot get used to this concept, you probably do not want to watch the rest of the movie. But otherwise, it's a cool movie. It uses contradiction in its own way. But in mathematical proofs, contradiction is a very powerful technique, proof by contradiction. Are there any questions about proof by contradiction? let me give you another one, another proof that you have to do, and you can do it by contradiction. Proof by contradiction. Let's say I have two types of socks in my drawer. Okay, because I go to Costco, every time I buy socks, I buy a big, huge batch of one particular kind of socks. Okay, so in the morning, I'm gonna reach into my drawer, and with my eyes already still shut, I'm gonna say, okay, I need to go find one pair of socks. How many socks do I have to pull out of my drawer? What is the maximum number of socks that I have to pull out of my drawer to get at least one pair?
4. We have 2 different types.
I have 2 different types. I don't care which type I wear on a particular day. I just need a matching pair. Okay, so how many socks do I have to pull out of my drawer to guarantee at least one pair? You're absolutely right. It's 3. Okay, so proof that it is 3, and not any number greater than 3.
Hide the board on you erase. That 3 is less than 2.
But how do you know that it's not 4?
Because it's 4 less than 3 underneath it.
That's not a proof.
Because
So let's, okay, go ahead.
Because since there are only 2 different types of socks, if you were to pull out any number greater than 2, it would have to be one of either A or B.
Correct. That's a direct proof method, but the proof by contradiction is saying, so let's say that we have to pull 4 socks out of the drawer just to get one pair, one matching pair, okay? Okay, so that means we have what? 3 different kinds. And that contradicts with my original claim that I only have 2 kinds of socks. So that's what the proof by contradiction means. Is you basically say, okay, what if that is wrong and I actually need 4 socks to make one pair? But having 4 socks to make one pair means there are 3 different kinds, which contradicts the original claim. So that's another example of proof by contradiction. If you're on the computer science degree track, the transfer degree track, I heard that there's a roadblock, in the process. So, that may not be reality anymore. Getting a computer science transfer degree, and you can apply to any CSU and UC. I heard there's a little roadblock. Some UC decided not to, conform to that standard. And so now, it's still up in the air. We have no idea, when everything is going to work out. But anyway, so if you're on that track, you have to take CISP 440, which is discrete mathematics or discrete structure. That's the class when we'll do a lot of proofs. In fact, that entire class is just mathematical proofs. It has no programming in it whatsoever.
Wow.
Sounds like geometry.
Well, it's just like any math class. It's all basically mathematical proofs.
That sounds like linear algebra.
Linear algebra, abstract algebra, they're all basically all proofs. Yep. The only type of question I don't like in a linear algebra class is when I actually have to invert a matrix. So they give me a 3x3 matrix and I have to invert it. I suck at those things, because I'm gonna make a mistake somewhere and then it would just make the entire solution wrong, right?
I just use my calculator during invariance.
Yeah,
They're
well,
always
back when
Let
I
the
took
technology do it for me.
when I took linear algebra, calculators could not invert matrices. In fact, they were not even allowed in that class, so I had to do everything by hand. All right. So, but what is the significance of this particular claim? I mean, after all this stuff here, the end result is this claim is true. Okay, so it is true. What is the big deal? What do you think is the big deal here? How does it relate to the algorithm that we were talking about? In other words, well, the algorithm is right here, and the claim is here. Why is it helpful? Let's take a look. Let's take a look at the spreadsheet here, and let's not look at the number this big or this insanely huge. Let's take say 23. Okay. And if you look at 23, it is a prime number, and it's we stop here because this is the time when f n mod f equals to 0. But my claim, okay, let me zoom out just a tad, probably a little more. Okay, the actual number is not does not matter, but my claim is if I use this technique, I can look at 2, 3, 4, and then 5, and I can stop right here and say that 23 is a prime number. All of the other computations are not needed anymore. Okay? Why can't I stop right there based on the theorem that I have just proven?
Because the product would be less than 5 times 5.
Because if it was a composite number, then one of the factors would have been less than or equal to 5. Okay? Is that okay? Intuitively, is everybody kind of relating what the theorem states to the optimization that I'm trying to work out here? If 23 was a composite number, in other words, if it was like a times b of some kind, and a not being 1 because we're trying to find prime factors, one of the factors, a or b, it would have been less than the square root of 23. So by the time I test 5, which is larger than the square root of 23, I would have found it already. The fact that I have not found a factor up to this point means there are no factors other than 1, but I'm not interested in 1. Is that okay? All right. So now that we know the theorem is useful, it's proven, and it is related to the algorithm that we are writing, let's see if we can integrate it into the algorithm to make it work. So what I'll do is I'm going to look at my favorite solution, which is this one here, and say, can we work on this algorithm a little bit and integrate what we just talked about in here? Well, it looks like if we want to integrate that optimization into the algorithm, we're going to change the condition. We want to get out earlier, right? Okay, so if you want to get out earlier, do you think we should use a disjunction or a conjunction?
Disjunction.
A disjunction is an or.
Yeah.
But with an or, you have 2 chances to make the entire expression true. With a conjunction, you have more chances to make it false. So do we want to make the expression false earlier, or do we want to make it true earlier?
False earlier.
We want it to be false earlier. So that means we want to use which operator?
Conjunction.
Conjunction, okay? Because conjunction makes something false, easier. Because conjunction means this has to be true. You know what? But the other one also has to be true in order for the entire conjunction to be true. So that gives me another chance of getting out of the loop, other than the original one. Okay? So when do I stay in the loop? When do I say that maybe there's another factor that I have not seen yet? F is the one that we are testing at this point. So how do I say maybe the next F, would still be in range and it can be a factor?
When f squared is greater than n?
When f squared is less than n. When it is less. So we have not tested all the potential factors yet. In other words, if n is a composite number, we are not done testing all the potential factors yet. It can still have a factor at this
Say
point.
less than or equal to. F is a
You're
factor.
correct. It has, well, if f times f equals n, then n mod f equals to 0 to begin with, and that would have taken us out of the loop as well.
That's true.
Yep. All right. So this is good. Okay, this is a fairly simple, optimization, except it doesn't work out completely, because if we exit the loop here. Now, if we exit because of this, hey, great, we just found a factor, no problem, that's the right way to exit. On the other hand, if we exit the loop because f times f is greater than n, that means n itself is a prime number, but at that time, f is not a prime factor of n. But the entire algorithm, the purpose of this algorithm is to find a prime factor of f of n. It's not to find out whether n is a prime number or not, but to find the prime factor. So we cannot just let it exit and say, well, it's a prime number. Well, I'm not interested in whether it's a prime number. I want to find a prime factor of n. So that means I have some cleanup work to do, afterwards, because I have to say, I have to say if f times f is greater than n, I have to do one little adjustment here by saying f is n, because the primary objective of this algorithm is to find a prime factor. So if n itself is prime, then it is its own prime factor. Does everybody understand why we have this conditional statement after the loop? Well, let's go ahead and just do it and see, how it works out with the optimization. Yep.
I know it's very simple, but my brain is having trouble catching up. The f times f, which is the square of f less than n, that catches it like you were showing us a second ago. It catches it rather quickly, so it doesn't just run through it.
Right.
How does it catch it again? It's trying to find the prime factor, or it's trying to make sure it's not a prime factor?
Okay, it catches, let's say you're dealing with 23, which is what the spreadsheet is displaying right now. By the time you're finished testing 5, and say that 5 is not a factor of, no, by the time you get to 5, you don't even have to test it. By the time you get to 5, you can make the conclusion that 23 is a prime number.
Right.
Because if it had a factor, that factor, because when you look at a factor, there's a duality to it, right? Because if 23 equals to a times b, okay, a is a factor and so is b. The theorem that I just proved said that the square of one of them, at least one of them, has to be less than or equal to 23. Is that okay? If 23 is a composite number, and it is a times b, a being greater than 1, because I'm not interested in 1 at all.
Right.
So if a is greater than 1, b is greater than 1, then a squared has to be less than or equal to 23, or b squared has to be less than or equal to 23.
Right.
And since I'm scanning the number from 2 and up, I would have come across at least one of them by the time I get to 5. So the fact that I have not come across a factor by the time I get to 5, and 5 squared is greater than 23 already, means that there won't be any factors. I'm done. If there was one, I would have found it already.
Okay.
Yep. So that's the premise of the optimization technique.
So that just it's like a shortcut.
It's a very good shortcut. Yep, it's a very good shortcut because as the spreadsheet is displaying, by the time I test 5, I can exit right away. But the problem is when I exit at this point, f, the variable f, has a value of 5, which is not what I want, because I want f to be a prime factor of n, and that's why I need the conditional statement to basically say if I get out because of the shortcut, I need to tweak it so that f does become a prime factor of n, because n is a prime number in this case. Okay, is that part okay? Kind of the general rationale of this. All right, so let's go back to the. Yep, go ahead.
So the whole point is to show that n is a prime factor to begin with when you run this.
That's what the optimization.
The optimization means if n is prime, you can get out way before the other algorithm. The other algorithm will have to run all the way up to n. So f in this case would have to go all the way to 23 without the optimization. But with the optimization, by the time f gets to 5, I can exit and say that okay, it's a prime number. There's no need to test anymore. All right. So this is a much better optimization than skipping just even numbers. Because if you skip even numbers, you're basically dividing the number of cases by 2. Okay? This is significantly better, especially when you're dealing with large numbers. If you're testing a number that's close to 1 million, that means you only have to test up to about 1,000 before you make a conclusion. So you'll be testing 1,000th of the other one if you're dealing with a prime number. Okay. All right. So let's go ahead and test this algorithm with a trace, just so that we can see how it works. Okay. And of course, I'm gonna copy and paste this one first, and then modify it to include the optimization. And we can turn this bigger again. f is less than n. That's the second condition. And then we have a conditional statement afterwards to catch the case when n is prime. Before we go any further, what happens when f times f does equal to n? What would happen? Now, if f times f equals n, then n mod f is going to be 0, right? So we are going to get out of the loop either way. But what happens to the conditional statement? F times f equals n will fail this condition because it is only testing for greater than. Is it really okay in that case? Yep. Because if f times f equals n, that means f is a factor of n, and we should report back and say that, yep, it is. That light was shining in my eyes, like,
Yeah.
oh, that's okay. All right. Let's go ahead and trace this. Okay, we'll trace it with both this test case. Well, this test case is not going to be interesting because it's just not going to work any differently. But this one will. Okay, so we'll try 13 for n. Copy and paste it. And use one to look at the algorithm, and then the other one to look at the trace. This trace is a little bit trickier. You know what? I'm going to do this. I have no use of any toolbars, so I'm going to remove all the toolbars. That I don't need for this class at this point, so I'm going to remove that and get rid of. I cannot get rid of the normal one. Fine. Delete more. That one I kind of need sometimes, but I can edit back later on. The reason why I'm doing this is so I can display the trace down here, because the condition is a little bit too wide. There we go. All right. So remove everything from the previous time and make the comments column a little bit wider because we will need more space this time. On line 1, f gets initialized to 2, just like before. On line 2, we test the condition. So in this case, we are dividing 13 by 2. 13 divided by 2 has a remainder of 1. 1 is different from 0 is true. But we have a second condition now. F times f is 2. 2 times 2 is 4. 4 is less than 13, which is n, is true. So now we have true and true is true. Go to line 3, add 1 to f. F goes from 2 to 3. Go back to line 2. 13 divided by 3 has a remainder of 1. 1 is different from 0 is true. So n mod f is different from 0 is true. F is 3. 3 times 3 is 9. 9 is less than 13 is also true. F times f is less than n is also true. So we have true and true again, which is true. We go back to line 3. We increment f to 4. We go back to line 2. N is 13. 13 divided by 4 has a remainder of 1. 1 is different from 0 is true. F is 4. 4 times 4 is 16. 16 is less than n, which is 13, is false. So we have true and false in this case. The entire thing is false. We get out of the conditional statement. Sorry? It's not true, right? Okay. The entire expression is not true. The first one is true, but the second one is false. When we get out of the conditional statement, we continue on to line 5 because now we have a conditional statement next to the loop. On line 5, we just compare f times f. F is 4. 4 times 4 is 16. We compare that to n, which is 13. 16 is greater than 13 is true. So we have to go to line 6 in this case. Line 6 is f gets n. So in this case, f, which currently has a value of 4, is being overwritten by 13. And then we get to post. So now f has the correct value, which is the prime factor of n. So are we doing okay so far with this trace and how the algorithm works and how it can get us out of the loop earlier by only going up to the square root of the number itself? Okay. All right. If that is okay, I'll just give you a preview of what we're going to do next, and also something that I found this morning. Okay, so we're basically done with topic 4 at this point, and we'll move on to topic 5. Topic 5 introduces a completely new concept that we have not talked about before. It is the concept of arrays. Actually, this is basic algorithms. I flipped the, okay, I have to fix the order because this is actually our next concept, which is arrays. We'll talk about arrays. There's not enough time to really get started with this topic, but what you guys should do is to start reading about it first, okay? So that on next Tuesday, when we actually get started with arrays, then you will have some idea of what it is, and then we can just kind of talk about the concept in class. But I do have something else to show you. I know you guys want to go because it's noontime. Yep.
Do we have the roll sheet?
Oh, row sheet. That's right. I forgot about that. That will take up, the rest of the time. But I'm going to show you something first, so to keep you guys entertained, so you guys won't feel bored. Where's the row sheet for this class? How many people are planning to take cisp300 in the fall? All right. I might see some of you because I'm assigned to teach that class this fall. So I'll be teaching one section. Damon Antos will be teaching one section, and then Iraj will be teaching another section. So for the first time in many, many years, I think for the first time in my entire duration here, this is the first semester we offer 3 classes in cisp300.
Do you know what time you're going to be offering it?
Yeah.
With mine, I think I know, but I cannot remember what it was. I think it's still in a hybrid format, which is not my favorite. Okay, so this is what I found earlier this morning. As you guys are waiting for the row sheet, and getting absolutely bored, I think this will help get through that boredom a little bit. I'm not familiar. I'm not affiliated with Zezo itself, but I think some of these comments is kind of interesting. I hate IE. How web developers see themselves. Some are probably not very class appropriate. Select shirt from dbo.closet where creased equals false. That's a SQL statement. Loading, please wait. But that's one that was really kind of funny. I mean, let me see if I can find that one. Yeah, the poop one is probably not very class appropriate. Eat, sleep, code, that one's kind of boring. Now that's one that talks about all the different types of programmers. Oh, maybe it was not here.
No, we have 14 pages. A lot of results. 840 to be specific.
And full bar is not even a term in computer science. Yeah, it was borrowed from the army. And it was not 2 O's to begin with either.
Yeah.
Okay, that's Ruby, that's PHP. Have no fear, the programmer is here.
It's an expensive shirt.
Yeah. 30 something
That's
dollars.
not
I know COBOL. Actually, this is funny because if you know COBOL, you can't afford a shirt like that. I'm not kidding. COBOL is a kind of programming language for business applications like printing, social security checks and stuff like that. But the programs that have been written in COBOL, those organizations, including the government, they are not willing to convert those programs into newer programming languages. So they want to keep maintaining these COBOL programs. The problem is all the COBOL programmers, some already have died. I mean, it's really that long ago. So imagine in the 50s and the 60s, okay? So we're talking about programmers in their 40s, in the 50s, okay? So they're pretty much gone now. So who's going to maintain these programs? They don't have anyone to maintain these programs because new people coming out of universities, they know C++, they know C#, they know Java, they know Visual Basic, but nobody knows COBOL. So they are now actually having a shortage of programmers, maintaining those old programs written in COBOL. So it's kind of interesting. I'm a programmer. They're all spelling mistakes.
Yeah.
I just write code. Some of these are not really interesting. I would not spend $23 to buy C++.
Didn't you have them print it cheaper? Did you go to a site where they just print it out?
No, you just go buy those iron-on type of thing. Print it with an inkjet printer.
Like this, when you become a member, you get emails of 80% off or 75%.
Oh, is that how it works?
So they have them at this high price, but chances are you could find a 75% off coupon code.
Yeah, I think the best T-shirts, the ones that I really like, but I still won't spend money on it, would be on wood. Sometimes they really have fun ones. Yeah, this one. Okay, I'm not sure whether you guys can see it or not. Remember in the caveman, drawing, they have pictures of how hunters kill the mammoth, elephants. This one is kind of depicting the elephant reversing that, it's chasing after the man.
But as it's
But sometimes they have really, really awesome teachers. There was one where they have the TARDIS. Okay, the TARDIS is the spaceship in Doctor Who. It's a time traveling, kind of thing. So they have the DeLorean from Back to the Future crashing into the TARDIS. That was funny. That was just funny. I was tempted to buy that one. But most people may not know what it means. It's like, oh, okay, there's a car accident in Britain, in London. It's like, no.
somebody actually had a DeLorean.
No, where's the roll sheet right now? So it's almost done? Okay. All right, I'll see you guys on Tuesday. Have a nice weekend.
Algorithm you traced. Why didn't you went to trace that and then you went back to line 2, but why didn't you just go down to the if condition?
Because if this is a loop, I can only exit when the condition of the while loop is false. So I have to go back here first before I move on.
Okay. Okay. That makes sense.
Did you get back to the test?
Yeah.
Sorry, I was,
the pile of tests should be right here. Yours is. It was difficult to read your name.
Yeah.
Okay. Thank you. All right.
The 9 a.m. roll? 9 a.m.
9 a.m. roll sheet.
Also test.
Oh, that's great. What's your last name?
Sheridan.
There should be. Oh, looks through this pile. I think it's in there.
So are these tests fully graded?
Nope. Once it's graded, your score will reflect on Moodle. I kind of like the concept of having the electronic version to begin with, because I can do the grading on anywhere I go. I don't have to bring a big pile of paper with me.
Do you have office hours now? Office hours?
Not right now.
Okay. Do you know any like books or anything about like security or Linux stuff? Security Linux?
Not really, but depending on how deep you want to get into the topic, if you just go do a search on Linux security tutorial,
Okay.
I would bet you can find really good tutorial material just going online.
All right. I just need better internet. I go to McDonald's. But
Yep, or Starbucks.
yeah, no, Starbucks. It's actually